Okay, let's get started. I think they passed out after lunch. They ate too much rice. So we were talking about the structure of the program, and we were somewhere here where I said that I'm setting up two sets of velocities, one for the edge of the triangle and the other for turning when it reaches the vertex. So this is the straight set, 0.2 meters per second, and the rotation velocity is 0. And then the turn set is here. You only turn, you don't go forward. So this is a very crude way to go around it because typically, stopping means you lose time. So this is just to establish the basic idea. Okay, so you got to get your down information just like you did in the assessment exercise 1, and then unpack and put it in X and Y. And then I'm getting ready to drive forward because I know the first motion is straight line motion. So I'm packing the container variable, the structure, B, L, MSG, dot, 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 with the set corresponding to the edge. Okay, I was talking about this when we ran out of time. So basically, if you don't want to use it, don't use it. But here, it's needed for another purpose. It's not just that you're running the loop at 10 Hertz. You also are using the time part of it. And you're using time to drive. So here, you can't throw out the whole thing. But in the second exercise, if you don't want to use it, then because you're not using time measurement anymore, in homework exercise 2, you can drop it if you want. So here's the Ross rate object, and then I have several loops. So first I'm going to go through the loops for this OLCL1 version. Then we run the OLCL1 version and see what it does. The fact that the triangle will never close, and that you get different, it's not even a triangle because it doesn't close, but every time you run it, you'll get a different result. And that is because it's not a jitter because we are canceling it out with the set model state command. It's because Gazebo adds some noise to the way the robot is run in order to make it realistic. Okay, so there are 3 loops. One is a for loop, and the for loop. So homework exercise 2 will also have 3 loops. The for loop is the number of sides. We have a triangular structure. So that's why the first for loop is running from 1 to 3 for each side. And for each side, you're going to do a straight line motion and then a turn. So one of those for loops does both a straight line and a turn. And so if you do it 3 times, we'll come back hopefully to the beginning again. Okay, then I'm calculating the time taken to travel this particular edge. Now remember, in general I might have different length of edges. So here I'm calculating the same number 3 times, because it's an equilateral triangle. But that's okay because this program can be used to generalize it for any structure, non-equilateral triangles. So I'm calculating TS as the length of the side divided by the velocity of your straight drive. So by the way, one reason that this will not work, which I forgot to mention, is that the robot is initially stopped. And it can't get from 0 to 0.2 immediately because it has some dynamics. Robot 3 is a very light vehicle, but it has some dynamics. So because of that, the first edge is where it starts to settle. Oh, by the way, no, we're stopping it after the first vertex. So every edge is faced with this problem that the robot is starting from a stop position. So there will be some time delay before it reaches the target velocity. So because of that, you will not be able to, complete the triangle. That's one reason, but also you don't have a closed loop structure. That's the other reason. So I fill the container variable, I start driving, right? And this is my time counter. I set it to 0 initially, and then I reset the rate object because it's like a stopwatch. I'm saying, okay, start counting now. And how far I'm going to count? I'm going to count up to TS. So why RTT less than TS, right? So long as I have not run out this time, I'm going to keep driving forward. And then after that, I'm going to figure out some new times for turning, and then I'm going to run a second loop, turn in place for SMS. So here's the second loop. So So you have a for loop, and then you have two while loops within it. Okay, so don't forget this. You have to get a fresh odometer reading, because if you don't, it will be as if the robot is not moving, and you'll never seemingly be moving towards the vertex. So these are all programmatic tricks, right? Initially, something doesn't work. It's not that the idea is faulty, but your implementation is not complete. So then you get into the debugging phase. So you have to develop the right logic first, which is the flowchart, and then you have to implement it correctly. So I get a fresh odom reading here. And then I unpack it again, right? And then I add to the X, like we did for the L. I augment X with that, and then I'm burning the rest of the loop time. I said you don't have to do it if you don't want to. I'm just burning the rest of the loop time because I don't want it to run this loop faster than 10 times a second. So when will it come out of this loop? When RTT is greater than TX. And so at that time you stop the robot because we're not going to turn on the move. So I stop the robot and now I'm ready to rotate. So I need to calculate how long it takes to rotate. And that is based on my angular velocity, right? Now be very careful. The angle was specified in terms of degrees. So if you want to match it up with rotation of turn or turn rate, which is in radians per second, you got to convert. So these little mistakes you'll make all the time, and then you'll figure it out eventually by getting printouts. See, that's why if you remove this semicolon, then you get the printout in MATLAB. Typically it's very annoying because they'll keep on putting numbers, but for debugging that's the only way you can figure out what's going on. You just put some intermediate printouts and see what's going on. So then I calculate the time needed to turn, and then I fill the new set of velocities for turning. So this is the velocity of turn, which is 0, and the rotation of turn, I think it was pi by 10. And then I say, okay, start turning. So again, I've got to initialize the time counter again. Again, that's a common mistake. You don't initialize it. So it's still sitting at the old value, right? So these are the debugging things you have to look out for. And then I reset the alarm clock or the counter, timer rather, and then I have a second loop. And basically that's it. Notice, I must keep getting the odom. Because otherwise you won't know that you're turned, right? You must get the fresh odom. And so when you say odom receive sub odom, it gives you like the latest frame of data. So if you miss some in the middle, because remember, odom is publishing at a certain rate, you have no control over it. But it doesn't matter, because only the last frame is important to you, right? You're not forced to process every single frame that it's giving you. And that's like in life, right? Maybe somebody is, talking to you and you have a tough traffic situation. You don't pay attention to what they're saying, right? So many things are coming at you at different rates, and you only look at the latest piece of information. Your attention is on the most important thing at any given time. And then you burn the rest of the loop time, and then you again stop the robot, because after the turn you have to stop, and then you go to the top of the for loop and do it twice more. And then when you finish the for loop, you finally stop the robot again, and then this is the same plotting code that you must have used for homework exercise 1, right? It's exactly the same thing. Is that okay? So this is an example where the program exits. Typically in robot programs, you have to hit a control C, because you're doing something forever until there is no need to do it anymore. So that's why I have a raw shutdown here. But in case you did a control C exit, then I have a raw shutdown up here. And shutting it down twice is not a problem. It will just say that it's already shut down. You won't even see it because it will be on the screen and disappear. So we'll get to the new logic in a minute. I want to run it. So my IP address is okay. I'm going to move this, or maybe I can run it and then minimize it. Sometimes you find it off the line. This time it seems to be not drunk. It's going straight. Once I found it somewhere, there's my mouse. It doesn't want to come there. mouse is stuck in the screen. Oh, because we put it in mirror. Yeah, that's right. No wonder. I'm in mirror mode now, so this is only screen. So there's a perspective problem here. So you can't tell whether it's doing it right until you look from above or you get the plot. Everything will look right. You see it's going approximately towards the origin. I don't think it's going to make it unless we get very lucky. It'll give a plot any second now. See, it missed. Yeah, definitely missed. The plot should come up. Oh, the plot is in MATLAB. So, yeah, there it is. See the crossed over? Sometimes it'll be open. Here it's crossed over. So if you run it many, many times, you get different things. Because I think gazebo adds some noise to it. That's what the real world is, right? If you take 100 steps blindfolded, you won't end up in the same spot. And that's what odometry is, yeah.
Why is it a break in that?
That must be a plotting glitch because it has not happened to me before. It must be, some kind of a plotting glitch. Okay, so if you got this, then I can use this, the program. So you have this program. You just need to add to it, and I'm going to verbalize it. If I give you the code, then there's nothing for you to do. So let's just talk through it. So you're not going to stop and turn. So there's only one set of velocities. Forward and turn, right? So you start out down so how do you drive typically, right? Typically you're not even pointed towards the goal. But if your program works, you can try misaligning the robot a little bit. Not point at the first waypoint. Remember the first waypoint is here? So it's not pointing at it anyway. It is only pointing in this exercise, right? So in number 2, it's not pointing there. But you can point it completely away in the opposite direction and it will come around if your program is correctly written. So what you're going to do is you're going to drive forward. And you're going to drive forward over a for loop which runs how many times? As many times as there are waypoints. So we have a waypoint here, and then we have a waypoint here, and then we have a waypoint here. So just by coincidence it turned out to be 3, just like this program. But you can try adding other waypoints. It's quite a lot of fun. Once you get the program going, it's hard to drag yourself away from it. The first time it works, you'll probably get emotional. I'm joking. It's fun to see something working like that, and then you play with the parameters and so on. Now, there's a critical part of this algorithm, which is the control loop, right? Pay attention to me, because if you choose a parameter too high, then the robot is going to be spinning around. It's going to be an unstable control system. I'll explain where that problem will arise. Okay, so you have a for loop to do the waypoints, which is 3 in this case. You can add on more if you like. And then inside it, there's going to be an outer loop. See, in this program, there was a while loop and another while loop, right? One below the other. No, here there's going to be a big while loop, and the orientation loop is going to be inside. So the big while loop is going to be driving the robot towards the next waypoint. And how do you determine whether you made it to the next waypoint? You're going to calculate the Euclidean distance from the current robot position. So remember, refresh the odometry, because if you don't, the current won't really be the current. It'll be the previous point, right? So refresh the odometry as you drive and check the distance to the first waypoint. Euclidean distance, you know how to calculate that? But otherwise you can use PDIST or PDIST2. They are built into MATLAB. I mean, that's one line of code, There's no advantage in going to PDIST. Now, if you don't turn, do you realize you'll never ever satisfy that condition? Remember we said 0.2 meters? So that's literally like drawing a circle around the first waypoint with radius 0.2 meters. So no matter which side you approach, right? Once you're inside that circle, it's like, I put my foot close enough, And at that time, you should go to the next index of the for loop, right? So you're going to check for the distance. However, if you don't turn, you will never reach that condition. You'll never be satisfied. You'll be permanently on the first for loop, right? So that is where you have to have the inner while loop. So, what do you do in the inner while loop? You're going to look at the heading, your current heading. How are you going to get your current heading? You're going to unpack. Remember I showed you the other program? You're going to unpack the quaternion for orientation. Quaternions are only for orientation, not for position. You're going to unpack it. So there are many steps here, right? When you unpack it, you get the quaternion, but then you have to find out the Euler angle corresponding to that. That Euler angle will be in radians. But it's nice to get it in degrees, because if you are forced to debug it and you want to print it out, and if you print radians to the screen, you'll have a hard time figuring out, okay, what does this mean? So I typically, I try to get it in degrees, right? And so that's your current heading, right? In other words, I'm basically saying, this is the program I showed you this morning, right? Remember this? Adjust heading. So essentially, everything you need is here, except that you've got to get the variables right. You know the current location of the robot, X, W, and Y, W. It may be called something else in your program, right? In your program, you may call it something else, but here it is, it's XR, YR. XW, YW is the next waypoint, right? So match the variables, because these are variables local to this program. So you're going to get the desired heading and the current heading, right? Here's the desired, and the current heading, which I wrote down here, is the number. So these you're going to have to do. I just made up a number here, right? It's not going to be 135. It's going to be unpacked from the quaternion side of your pose, right? So I think here, Euler to quaternion conversions. Try out something. Typically, people jump to a 100-line program. The beauty of MATLAB, unlike C++ and C and Python, well, not Python. Python is just like MATLAB. The beauty is you've got this calculator, super calculator, right here. So you can try out little things. You can ask for the quaternion, right? And by looking at gazebo, what is the angle? What is the heading, right? You can twist the robot and set up a certain angle and do your code testing in the window here, right here. And then once you're happy with it, you can take that code and put it into the program. You know what I'm saying? So the 135 that I made up here has to be read off the quaternion for the pose. So remember, you must have refreshed in the immediate past. So don't worry if you have done a few lines of code and then say, oh, maybe I didn't know. Because that code just flies. So once it's been done, in the vicinity, it's okay. You'll have the most recent heading. So then you'll calculate the difference between the two. Is it okay? And then what are you going to do? So here's the control loop, which probably depends on when you had a control theory class or if you had one at all. It's going to be the most difficult challenge. Most difficult or least easy. Let's say it's not that difficult really. It's the least easy. So you've got the angle difference, right? Now this is in degrees. So let me open up a browser window here. Oh, yeah. So you're going to change omega, right? It's not called omega, right? You have to put it into that variable you're using to set up V and omega, right? I'm just using omega because it's a turn angle, right? If you put omega and say, what is this omega? So omega is equal to, it became a capital omega, but you get the idea. Omega, W. So proportional constant times error. So you want to set up a control loop where the turn rate is based on how big the error is. So the turn rate must be based on how big the error is. You don't just want to say, my error is negative, so I need to turn this way. You want to size the reaction. Do you understand that W is the reaction? You're reacting to the error, right? So suppose you're going like this, you want to bring the wheel around this way quickly. But if you're only here, then you want to bring it around slower, right? That's how you drive. You don't always drive like this, right? So just enough to correct it, but otherwise, if your car is, you've fallen asleep and you're going into this lane, then, you will pull it over faster. So this is the classic proportional control. So this number has to be chosen carefully. So when I ran this program like 3 or 4 days ago, the robot went into a spin. So first of all, you got to debug and fix all the other issues. And then I said, it's got to be this. How did I know that? Because I got this W printed out. It was huge because I think I put a number like 1 there. So it's smaller than 1. Hint to you. It's smaller than 1. How much smaller, you'll figure out by trial and error. But make sure everything else is working before you start tuning this. So when you print it out, you'll see that you need a reasonable value. You can't make it like pi radians per second is 180 degrees per second, so it starts spinning. So it has to be smaller than 1, and then it works beautifully. It will go to the first waypoint, and the second waypoint, and the last waypoint up to stop. And you can add more waypoints if you want. You can make that circle for achievement of waypoints tighter. Sometimes, if you make it too tight, it might not achieve it, and that's real life, We can't attain all accuracies that we demand, we cannot. Then you have to put more money into the system, You have to have very careful heading control, right? If you make a circle like this and say, unless you get into this, you haven't made it here, then it means that you haven't aligned finely enough. So you have to have a system that gives you fine alignment. So by the way, on Mars, they often identify rocks that they're going to go and collect, and they have to come at it from a certain angle. So the control has to be super fine. Those control systems cost hundreds of thousands of dollars. So they have to come in at a certain angle because they got all these tools that they're using to collect the samples. So alignment has to be precise. It's not like they just pick, okay, let's drill here. Everything is pre-planned because the whole mission costs billions of dollars. So it's how much money you need for that particular task. That's what the control system needs to be. So I think I've explained pretty much everything. Any questions? Okay. You're doing okay with respect to the homework exercise 1, or you're going to start tonight? Okay. All right. So let's go to the next topic. Let's just run it one more time. I'm curious what happens. So you can see it's, you see where it's missed, right? So you don't have to do anything because I already have a reset set model state, code there. So hopefully, if I wanted to show it snapping back, but you can try it yourself later, but it will snap back wherever it is. Okay, there are too many steps for me. It's already moving already, I think. No? What happened? Oh, I did not start it. Why is my... Oh, I'm running the wrong program. I'm on a different screen. I'm not on OL CL1. Left wheel seems to be on the red line now. No, very close to it? No, it's okay. At least from this perspective, yeah, it's missed a lot. Yeah, definitely. Not a lot, but it's more than the previous time. Close, but it's moved a little bit, I think. And there's no gap now. We're asking about the gap. So maybe you want to make this line a little bit thinner. There is a way MATLAB is doing that with the plot routine. It's a little bit too thick. So see where it ended up? It started at 0, 0, but it ended up at 0.40. Any questions? So if you use this program as a building block, that is the best way to get the second exercise done. So you have to do it a little bit at a time. You know, you can't just build the whole program and say test it. Okay, why is it not working? You have to. That's why I throw in so many comments and I space out my statements and so on. It's worth it. You know, it's like it should be properly formatted so that you can see the key pieces of information. I separate blocks that are doing something from other blocks that are doing something. So that's really how you should write code. Okay, now we're going to switch topics and go to coordinate transformations. I posted a couple of documents. You can take a look. I'm going to pull it up any minute now. Coordinate transformations with quaternions. Now you don't want to go through, in fact I heard you've already gone through a discussion of coordinate transformations in your class. So we don't want to do that part of it, the standard part. We'll do the quaternion part because that's new. First we'll see what the problem is if you don't do quaternions. So there's a thing called gimbal lock. I already talked to you about the wrap problem. You know, that's not a major problem. It's just, you know, every time if you add 360 degrees to your angle, then the robot, instead of going here, it's going to spin all the way around and come this way, you know, which is an odd way of, you know, moving. So that's a minor problem. The wrap problem is a minor problem. The bigger problem is you get something known as gimbal lock, which I told you in Apollo 13 it was a problem, and they had to figure out a way around it while they were in the air. You know, that was 50 years ago. But nowadays they try to think everything through so that they have gone through the possibilities. You know, what could possibly go bad, and then, you know, how could you fix it if it happens? You know, kind of a thing. Okay. So, characterization of translations is easy because the number scale goes from 0 to minus infinity to plus infinity, right? So there is no ambiguity. Whereas angles, they come back around, you know, from minus 180 to plus 180, and then it jumps back to the minus range again. So if you look at those numbers, you'll say, oh my God, something drastic happened to the robot. You know, it was pointing at 180 or 179, and now it's at minus 179. But that's not much of a change, really, right? So that something has to be done about that, because we can't treat that as disaster, like somebody hit the robot and spun it around or something, because it's only a tiny change brought about by the representation, right? It's 179 minus 179 because of the chosen representation. So the range of angle representation is finite, so that's what is causing the problem. One of the best approaches, the most intuitive, meaning most natural for human beings, is using Euler angles. So if you have a body in space, right, then 3 angles characterize its orientation. You know, because 3 degrees of freedom, you need 3 angles to figure it out. But it causes the problem of gimbal lock. I have a video to show you what gimbal lock is. This is not an easy thing to understand, you know. They tend to talk very fast in these videos. But basically what happens is, for certain axes of representation, 2 of the axes align with each other. In the process of rotating it, right, 2 of the axes align with each other. What does that mean? It means that you can't independently separate them. That is, you need two numbers, but they're aligned. So you don't have three numbers now anymore. You've got the 1 plus 2 of them are the same because the axes are aligned, right? So because of that, you lose a degree of freedom. So obviously you cannot represent it uniquely. And what that does in the process of the traditional, remember the matrix transformations of the traditional method of transforming them, that matrix will blow up. So if it's not blowing up, it means that we are not hitting gimbal lock. We are just lucky. Let me give you an example of when this may happen. So let's say you have a camera on a moving axis, right? If you choose a certain set of axes, we'll see what they are. And if you point the camera at the roof, you'll get gimbal lock. If you point the camera at the floor, you'll get gimbal lock. So the fact that you're not getting it means what? You typically don't have to point the camera at the roof, right? You can stop here and you can stop here and you can get by, you can get your work done. So gimbal lock may not be occurring because you're not doing this extreme thing here. But watch out, even as you get close to 180, the numbers in the matrices will start to become big. So it's not something that happens exactly at 180. The numbers start to get big even as you approach that critical vertical up and vertical down for the camera example. So if you're only going from here to here, then you're okay. You will never encounter gimbal lock. You don't even have to worry about quaternions, and life is much more happy without quaternions. So quaternions overcomes the gimbal lock problem. If you had a quiz question, they said, what is the use of quaternions? What is the biggest use? You'll say it eliminates gimbal lock. Okay, so here's an example of Euler angles. A sequence of 3. Sequence. It cannot be in any order. So a sequence of 3 rotations around the 3 coordinate axes. So for instance, if this is the base and the plane is somewhere here or here, right? You can represent the plane going from here to here by a sequence of 3 of these rotations. Well, let me change that. That doesn't do translation. So I said here. No, that's not true. Let's say the plane is right here, but now it's twisted. So it's in the same spot. Translation you have to do separately. So a sequence of 3 angles will represent that rotation. Can I say one thing about the second exercise that just popped into my head? So I want to connect it to the first exercise, right? There, you're driving on a circle because you want a certain shape. Can you drive on a circle to get to that first waypoint? Yes, you can. You can figure out a circle that goes through that point. But how will you do it, right? You have to sit down and calculate, you know? Or you'll have to say, let me just drive on a circle and see whether it goes this side or that side. And then I'll adjust the radius until it goes to that first waypoint. That's not a good way to drive. Plus, you're not going to go by the shortest path. You're going to flare out and come like this. That's why you need a control system, and you need to change V omega instantaneously, constantly. And what does that mean? You're putting together little tiny circles. So you're threading the path by, you're using threaded tiny circles to create the path. And that's what we're doing all the time when we drive, actually. Each little thing is a circle. But then you have to change the circle because, you know, if you're in Chennai and point it this way, right? You can't say, I'll finish the circle and get to Mumbai. Because, you know, the cab fee will be too high then, you know, if people drive like that. So it's a sequence of 3 rotations around the 3 coordinate axes. So this is the classic, what is the order? Yaw, pitch and roll. So yaw is like, so imagine I'm a plane. So yaw is like this. That's the name given. Pitch is, you know, forward and back. You know, in ships, when the boat goes like this, you feel like vomiting, right? It's this motion that kills you. This is not so bad for a summer. And then roll is, you know, completely this way. So yaw, pitch and roll in that order, as represented here, is one system. It's an ordered sequence. You cannot change the order. That's what the word commutative means. The order cannot be changed. And here's a statement from Wikipedia that shows you how difficult the system of axes can be. There are many, many, many systems of axes. The 3 elemental rotations, that means yaw, pitch and roll, right? Or any other ordering that you choose, may be extrinsic. So extrinsic meaning that these could be with respect to a fixed axis system. In other words, you don't take the axis with you. But typically in a plane, you take the axis with you. So when you go like this, right, the axis also goes with you. Otherwise it'd be useless to the plane. If you leave the axis behind, it's called an extrinsic system. If you take the axis with you, it's called an intrinsic system. So that by itself produces two pathways now. You can do it like this, extrinsic, or you can do it like this, intrinsic. Extrinsic systems are not that useful. Because when I am rolling, I want the axis to be, embedded in me. I don't want to leave the axis behind just because I roll this way. Because it'd be very hard to represent motion from your point of view. So but that creates two separate systems of axes that if you want to use it. So the three elemental rotations will be extrinsic, rotations about the axis of the original coordinate system, which is assumed to remain motionless, or intrinsic, rotations about the axis of the rotating coordinate system, x, y, z, which is fixed. Solidary means fixed to a moving axis, a moving body. So now this is going to blow your mind. So these are just 12 examples. There are many more, but these are kind of interesting. Now how do you get these 12 orderings? Because I'm taking 3 of them. And then I'm forming all the combinations. Now, normally if you take 3 here, 3 here, 3 here, you'll get 27, right? But it does not make sense to put x and x together, because if you have x and x, why don't you add the 2 x's together and do it in one motion, right? You know what I'm saying? X and x will add up anyway, right? So what's the point of having an x and x? So repeat axis or removed, And then if you remove the repeat axis, there's only 3 possibilities for the first position. There's only 2, only the other 2, right? And then the last one, right? You can go back to the first one again. So if you look at it, the 2 cases of non-repeat and repeated axis. So here's repeated axis, x, cx. So you can repeat it after you've done something in the middle. So the repeated axis can only be in a sandwich. You know what a sandwich is? See, this is a sandwich, x, cx. So you can repeat the axis. You can't repeat immediately because that doesn't mean anything. You can just add them up together. So here is a repeated axis with z in the middle. So it doesn't even have y. You don't need it. If you actually do it, you'll see that xzx works. You don't need the y actually. So here's one that is not repeated, x, y, z, all the possible combinations, zxy, xzy, etc., etc., etc. So it gives you a total of 12 cases. And then when you go to extrinsic, and so dynamic is the same as moving or there's also intrinsic, so it becomes 24. I don't want to spend too much time on this. I want to get to quaternions. So MATLAB uses the Yorpix roll ZYX system by default. So Z is first, Y is next, and then X is third. That's the order. So if you didn't think that was your order, better change it, because MATLAB is going to think that's the order you wanted. So you have to agree with MATLAB, or you have to change its axis convention to yours. So you have to agree in some way. And it is an intrinsic. The axis moves away from the original position. So it is an intrinsic. You can set up extrinsic axis if you want. And I just threw this in there. The way to really understand this, but as a medical robotics student, you're not interested. But somebody who's in CAD or something, you need to take a die, a dice. It has numbers. So the reason is you don't use a cube, because after it's rotated, you say, okay, where did this face go? They all look alike. So you have to have a number on each face. So if you take a dice, and then do it, you will understand what's going on. So it's very simple. That's why people use it. It's very human. The way humans read orientation. Only 3 numbers for the 3 degrees of freedom. Now, what could be better than that? For 3 degrees of freedom, you need 3. But quaternions has 4 numbers now, right? There's a W, X, Y, Z. Only because it helps you get rid of gimbal lock. It's worth it. Now, this is I thought a nice thing to throw in there. When you work with Euler angles, you know where transformations are used? A lot. So it's used in the world of, the game creators, video game creators. It is their bread and butter, transformations. Now why is that? It's because they're drawing these cartoon characters, right? And there's somebody with a sword and he's coming down like this on the head of the villain. Or maybe the other way around, the villain on the head of the hero, right? Now how do they create these intermediate positions? They're picking up rotation angles in between, except that when you interpolate linearly on Euler angles, the motion is not linear. There's a non-linear mapping between the two. So it's very odd, you get odd motion. So Euler angles, they don't allow for continuous interpolation of motion. So what these older gaming guys did is, they figured out how to compensate for that. So they have this vast libraries of software that they use, and they figured a way around it until quaternions came around. Quaternions interpolate smoothly. So the property of the quaternion is it interpolates smoothly. And there is a division in the gaming world. The older gamers, they don't like quaternions, they don't understand them. Of course, they're smart enough to understand them, but they prefer not to use them because it's something new. All of us, we don't like new things. So the newer, younger people, they use gamers, the game developers, they use quaternions because the motion is much smoother in interpolation. So now we come to gimbal lock, and then we'll just show a quaternion example, and then we'll move on. So you can see this one, I found this more recently. She talks very fast, and maybe you'll have to play it slowly for yourself, but I'll point out the key aspects of it. Gimbal lock occurs when the pitch angle is plus or minus 90 degrees. So let's look at this. That is the thing. Here it is. So the pitch angle, right? So when it comes down 90 degrees or the other way around, because it's a moving axis system, you'll have this problem that two of the axes align with each other. So that's when it happens. So, by the way, gimbal lock cannot occur on flat planes, only in 3 dimensions. There is no such thing as gimbal lock. There is the wrap problem, the angle wrap, but there is no gimbal lock problem for motion on a flat plane. So when you get a pitch angle of plus minus 90 degrees, both yaw and pitch will represent the same rotation. And the matrix, if you're using the standard way of transforming it, will blow up. And that's the example of the camera, try not to make the camera look up and down, and typically you don't have to look at the sky and the floor, so you're okay. We already know this, the red axis, green axis, blue, so I skipped this. So before quaternions, there was another representation known as axis angle representation, and you will find the quaternion representation is very similar to the axis angle representation. So what is the axis angle representation? So you see here, there is a plane and there is a rotated plane. So we can look at this in 2 ways. We can say, it's already rotated. Can you find a single axis, that means a direction, and an angle that takes this plane and puts it in this orientation? And there is a way of doing that. It's known as Euler's rotation theorem. So you can figure out, and apparently this is true, that any rotation can be characterized by doing a certain rotation around an axis, and you can find the axis and the rotation. So Euler found this out, that you can take this plane and put it anywhere if you find the single axis of rotation and the amount of rotation. Okay, so this is it. So it's a unit vector. In this system, it's a unit vector, which means that square root of kx squared plus ky squared plus kt squared is equal to 1. That's it. So the unit vector is just giving you a direction. And then the angle is saying rotate about this, and the plane will come to this position. So I want to point out 2 aspects of this. One is, you have a rotated plane, and somebody says, hey, tell me the axis around which if I rotate the original object, it will land here, right? The second one is, you say, okay, I want this plane to go here, right? Make the rotation. Make the plane, rotate into that position. So one is asking the backward question. The other is saying, I want this plane to go there, tell me how I should move it there. So we're not going to discuss how quaternions were derived. That's too much to discuss. In fact, I'll tell you. So there's a series of 6 videos. If you have nothing to do this summer, you can watch these 6 YouTube videos. Actually, the first 5 are the most important. The last one, it goes off track. So about 10 years ago, I spent an entire summer. I was in Chennai at that time, watching these videos over and over again. And it took me like 5 or 6 passes before I could get my notes down. I don't teach that in my classes anymore because I would be, driven out of the city by the students. Because it's very hard to understand. But if you are interested in how did this come about, well, there are 5 videos. The last one is not that relevant, and you can go watch it. See, that's why I put sweat. I was sweating because it was very hot in Chennai summer. So we're not worried about the theory of quaternions. We want to know how to use them. Okay. Now, it's always, I like to tell stories, right? So the great mathematician Hamilton, who was from Ireland, discovered quaternions. So he always thought that just like complex numbers, you're all familiar with complex numbers. You have a real axis and an imaginary axis. So he thought that in 3-dimensional space there should be an extension of complex numbers, just like x plus jy. He wanted a similar system for 3 dimensions, which led to quaternions, by the way. But he was missing a key ingredient. Whenever you create a new number system, the new number system has to obey certain rules of mathematics. I'm just going to give you a simple example. If 2 times 3 is 6, then 2 plus 2 plus 2 should also be 6, right? It's some kind of internal consistency that the number system should have, and he was missing that piece of information. And so he never published that work until he got it. And that's why there is the picture of this bridge. So it's the Broom Bridge in Ireland. So apparently he was walking across this bridge with his wife, and then suddenly she realized that he was not even listening to what she was saying, because he was thinking about the problem and he got that final piece, and immediately the quaternions became real. So it says right here as he walked by on the 16th of October 1843, Sir William Rowan, something in a flash of genius, discovered the fundamental blah 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 quaternions. So you can blow it up and see. I'm not able to distinguish the letters there, but it's right here on the side of the bridge. It's a famous bridge, it's historical. So his wife forgave him because he saved humanity, and of course he made the lives of many students miserable by coming up with quaternions. Okay. So, to summarize, it's a convenient mathematical notation for representing 3D orientation rather. It's a very simple construction, but very hard to interpret. You have to go through the 5 videos to understand it. That guy broke down the math for everybody to understand, but it's still difficult. You have to view his videos several times and take notes. Gimbal lock problem is eliminated. Now we did not see what gimbal lock is because we skipped it. So let's go back here and look at that.
In this video, we're going to take a look at the Sonnet Echo level. This dock is the perfect solution to expand the connectivity of your Thunderbolt 4 enabled device.
It's okay. It's nothing to be ashamed of. It happens to everybody at some point. It's perfectly natural. I'm talking about gimbal lock, of course. I'm not sure what you have in mind. So if you don't know what a gimbal is, today is your lucky day because I'm about to tell you. A gimbal is a suspended support that can rotate around an axis. Most commonly it's a ring. This Euler gimbal is the one that you're probably most familiar with if you're in the 3D animation realm, which we use for rotating objects and has gimbals nested inside one another, and a particular hierarchy. Each ring can pivot around an axis, so that the entire gimbal system can rotate on multiple axes. Gimbal lock is when 2 of these rings have been rotated in such a way that they both align and start to rotate along the same axis.
But there is a parent-child relationship. The outermost ring, when you rotate it, everything rotates, right? No problem. The middle one, when you rotate, only its child rotates, not the parent. Already you have a problem. Because when you rotate the middle, you can make the innermost ring align with the outermost ring, which means that you have lost a number. orientation is 3 numbers, right? But if 2 of the axes are aligned, then how are you going to get the 3 numbers? So those matrices, they get confused. They don't know what to do, and it's manifested in the form of infinity and crashing and so on.
In 3D animation, that means some whack shit is bound to happen in your rotations and interpolations, because the software is trying to interpret how to get around the issue. The thing is that it's really important for you as the animator, or as the rigger, to pay attention to the hierarchy of the rotation order of these gimbals to avoid the dreaded gimbal lock. The hierarchy is that the outermost ring is the parent, the middle ring is the outer ring's child, and the innermost ring is the child of the middle ring. So you see that the innermost ring can rotate independently, but is also affected by the rotations of the 2 outer rings. The middle ring, when rotated, will also rotate the innermost ring, and the outer ring, when rotated, will rotate all 3 rings. Now, you might be wondering where Euler rotation comes into all of this. This dude, Leonhard Euler, was a mathematician, physicist, astronomer, all-round overachiever. Genius. And he figured out this rotation theorem, which is that when you have a rotation system in 3D space, it has these axes, the X, Y, and Z axes, that rotate around a fixed origin point. So the gimbal is the axis system used for performing Euler rotations, and hence why this is an Euler gimbal. Now, there are different Euler rotation modes in your gimbal which depend on the hierarchy I mentioned earlier. We have 6 possible modes or hierarchy combinations according to the axes we have to work with.
We have more than 6.
X,
We
Y,
just
Z,
using 6.
X, Z, Y, Y, X, Z, Y, Z, X, Z, X, Y, and Z, Y, X.
She's not repeating
rotation
axes.
modes.
That's why.
These are named for the axes in order of the hierarchy they're in, starting at the bottom of the hierarchy and ending with the axis that's at the top of the hierarchy. So for example, in this one, X, Z, Y, X is at the bottom of the hierarchy, Z is in the middle, and Y is at the top of the hierarchy. The big cheese of the axes in this rotation order. You can see how easily you can get into the situation of gimbal lock. So I have this rotation manipulator here, right? And I'm going to change the transform orientations from local to gimbal. You might wonder why I don't just leave it at local, since when I'm in local and I rotate the manipulator, the X, Y, and Z axes seem to stay in.
So that's because it's a fixed axis system. With a fixed axis system, you cannot get gimbal lock. It's only when you take your axis with you, you run into this problem of gimbal lock.
Or distance. So it stands to reason I wouldn't experience gimbal lock, right? Unfortunately, that is just a visual representation, and the software still calculates with Euler rotations. So gimbal lock would still occur. So it's better to have it set to gimbal so you can actually see what is really going on. So I change it to gimbal so that it'll get an accurate representation of the axes. And if I go to my object properties, I can see that it's set to X, Y, Z Euler. So X is at the bottom of the hierarchy, it's parented to Y.
You see that? For us it is ZYX, but they represent that as XYZ. That's why it's so confusing in the world of engineering. Because ZYX, we write it in the order, she's writing it in the opposite order. But it's the same thing.
And Y is parented to Z. Z is at the top of the hierarchy. If I grab Y, the green one, which is the middle axis here in this gimbal that's set to X, Y, Z Euler, and rotate it, you can see straight away I've become gimbal locked because X is a child of Y. So when I rotated Y, X rotated as well. And now X and Z are aligned and rotate on the same.
So that's the idea. When 2 axes align, then you've lost that degree of freedom. You cannot do anything with that third dimension because it means the same thing as another dimension. And so obviously a program is going to be confused because it has only 2 numbers and yet you're trying to give it all kinds of orientations in 3D space. It's not going to work. So you can watch the rest of it. So let's go back and finish up now with the PowerPoint. But I just want to make sure of something. I went through the adjust heading, right? So that's a piece you need for your second exercise. And I also went through this Euler quaternion conversions. So you're going to have to borrow these little concepts and bring it into your program. You got to do that, and then that's how you'll be able to construct the whole algorithm. Using OLCL1 as a base, don't miss out on the degrees to radians conversion, right? And when you're giving a rotation command, you can't use your omega with degrees, right? Because omega is a radians per second. So you have to again convert back temporarily to radians. So there are a lot of tripwires along the way. You have to go slowly. Okay, so back to the PowerPoint. I lost the PowerPoint. Yeah, apparently it got closed. I hope I didn't delete it. Oh, that is a PDF. Sorry, that's right. Yeah, it's not a PowerPoint. So this is big, the smooth motion interpolation. For gamers, it's like heaven sent. Because in the early days, they were compensating. They realized that the motion was jerky with Euler angles, and they were trying to compensate for that by interpolation, right? So this is so much easier because it naturally interpolates to smooth motion. Okay. All right, so here it is. So this is a quaternion. It's made up of a scalar and a vector, but remember Ubuntu flipped the order, and I think they put the vector before the scalar, so be careful. W, A, B, C. So the XYZ notation in Ubuntu was misleading. It has nothing to do with position. It's just, that's why I call it ABC here, because then you're not confused instead of XYZ. So this is what it is. So first, let's just look at it. So, what is this? So W is cosine 0.5 theta. So remember, I told you that this is sort of like the axis angle representation. Here it is, right? Except that the vector is a unit vector, right? So square root of kx squared plus ky squared plus kg squared must be equal to 1. That's the only difference. But no, that's one of the differences. There is still an angle, right? However, that angle in the quaternion representation is embedded right here. See the angle here, the angle here, the angle here, and the angle here. Now, somebody say, why? Go through the 5 YouTube videos. That's how you find out. It's not an easy question to answer, in 1 minute. So, that angle, cosine 0.5 theta is W. And sine. So basically it's a scaling factor, right? So what is the direction of the vector? You might as well throw the sine and say Vx, Vy, Vz. Similar to the axis angle system. Remember, it had also 3 numbers representing the axis, but there it was a unit vector system. Here it isn't. But it doesn't matter. It's still a direction. These 3 have nothing to do with the direction because they are present in all 3. So the sine of 0.5 theta cancels out. It does not change the direction. But the quaternion system demands that they be present there. So if you're given a quaternion and you want to find the corresponding angle to, remember that angle is at one angle and then one axis. If you rotate it, this body will become like this. So if you want to find out that one angle, you do a 2 cosine inverse W. Or get MATLAB to do it for you. Now we're going to go through, this math is not necessary for us. So when you multiply 2 quaternions, we'll be doing that. I'll show you a MATLAB program. When you multiply 2 quaternions, the result is another quaternion. So W1, A1, B1, C1 is one quaternion. Here's the second quaternion. The product of the 2 quaternions. This is not a matrix operation. It's not like multiplying scalar numbers. It's known as the Hamilton product. It is in honor of William Rowan Hamilton, who discovered quaternions. So it's called a Hamilton product, and it's W1, W2 minus A1, A2 minus B1, B2 minus C1, C2. That is the W of the product. The A of the product is all of this. The B of the product is all of this. See, it's obtained from these and these, right? W1, B2 minus A1, C2, and C of the product is this. Q1 times Q2 is not the same as Q2, Q1. The order is important. So you know where this is going to come in. if you accept that a quaternion enables you to rotate, right? So I have a world frame and a robot frame, and then the robot is carrying a camera. The camera sees something, right? I want the world to see it. That's where you'll be using the quaternion, two quaternions in it. First you'll bring it to the, you'll rotate it into the robot's axis, and then you rotate it to the world frame axis. That's where you'll have a Q1, Q2. You can do 3, 4, any number of times. But the order is important. Camera to robot frame to world frame. And then it can go to a different robot, right? From the world frame it can go to a different robot and a different camera. But you have to maintain that order. Is everyone clear of that? So series of quaternion multiplications will take care of multiple transformations. The translation is handled just like before. It's only rotations. The translation you have to do just like before. So this is a problem I'm going to show you, then we're going to move on to the next topic. And maybe at that point we'll have a 5-minute break after we finish this. So this is what we're going to do. We're going to take a vector in the local frame of reference, and then there is a quaternion that represents the orientation of the local frame with respect to the world frame, and we're going to get a vector in the target frame. So we're going to transform from the local frame to the world frame by using the quaternion representing the transformation from local to world frame. It's always subscript to superscript, right? Local to world. Subscript, superscript. And that operation is written like this. So, here's what's going on. It's these 3 quaternions multiplied together. But wait a minute. The vector is not a quaternion, it's only 3 numbers, right? The vector in the local frame and the vector in the world frame, they're only 3 numbers. Well, if you see those 5 YouTube videos, he shows exactly why you have to take the vector and make a quaternion out of it by adding a 0 on top. So vector 3 numbers, quaternion 1 number, which is a 0 in this case. Why a 0? Why not infinity? You have to see the YouTube videos. So you take the local and pad it with a 0. Then you pre-multiply. That means a Hamilton product with QLW. And then on the back side you create a sandwich with the same QLW but the inverse of it. I'll show you what the inverse is, okay? When we do the MATLAB problem, you'll see. It's the same vector pointing in the opposite direction. So you take this vector and then you point it in this direction, which means you reverse all the signs. Isn't that right? So if you have a vector pointing this way, I want it to point in exactly the opposite direction, I put minus, minus, minus. So that's what it is. And sure enough, you'll end up with a quaternion, and the first number will be a 0. And what you need to do is you need to extract the last 3 numbers, and that will be a result. You'll see it in action now. You don't have to take my word for it. So that's why I stopped doing the derivation in class, because students want to know how to use it. At least this generation of students. I could not stand it during my student days if somebody just said, take this result. Because we thought differently. I wanted to know the why of everything, but there isn't enough time in this world to figure out the why of everything, because life is fast-paced now. So we have to learn how to use it and move on. All right, so I will show you the example and then we'll take a break. So, okay, I think it is HT2. So let's see. Yeah. So, like this. I want you to see both. So I made up a problem. This is the beauty of transformations, both with Euler angles and quaternions. You can make up your problem. You can create 2-axis system, and so long as you keep them like 90-degree rotated, you'll be able to see what the answer is, right? Now, of course, if it's not 90-degree rotated, it's going to be difficult for you to know what the answer is. But you don't have to. You can manage with examples that are 90-degree rotated. And then if it works for that, it will work for everything. So, world axis, here is the point, or the vector to be transformed. Is that okay? So it's at 0, 0, minus 1. See? 0, 0, and minus 1 along the ZW axis. Now, the local axis, there's no translation. If there's translation, you'll handle it by the conventional method. I just pull them apart because if I draw everything on top of each other, you'll be confused. I'll have to use different colors and all that, right? So I just pull them apart so that it's clear. So, this is the new axis. I know the answer, don't I? Because it's 1 below in this direction, right? So obviously the x, under the new axis system, the x local should be 1, right? Why 1 and not minus 1? Because xl is pointing down, right? I'm just reading off the answer, 1, 0, 0. Does that make sense? Now I'm going to go and generate the same result with quaternions. Do you understand what I'm doing? I'm creating an example whose answer I know. And then I'm trying to prove that that method works with quaternions. Also, notice, a pure frame rotation is executed, right? So, what is the rotation between these? Who can tell? See x here, and x is here, right? Y hasn't changed, right? So isn't it true that if I rotate around y, then I can align the two together? So I know what the alignment is, right? Remember that theta angle? I know what that is. So here is the, so I tried out multiple examples, that's why I commented this out. V local is 1, 0, 0. So, 1, 0, 0, correct? Oh, I'm sorry. I acted as if the problem went from here to here. Actually, the problem was given here, and then it went there. I don't want to confuse you. We're going from local to world, right? I acted as if we were going from world to local, right? It's like we're actually going from local. You can have it the other way around if you like. But we're actually going from local. So this was a given problem, and I should have read off the values on the word system. So I hope I didn't convince you, confuse you. Okay, so V local is 1, 0, 0. See here? 1, 0, 0. Enhance it, remember? There's a vector of 3 numbers, right? I got to pad it with a 0. So I put a 0 and create a quaternion version of the local. Now what is this? Do you remember, or should I go back to the PowerPoint? So cosine 0.5 theta, right? And then we had the 3 vector elements, right? Now let me show you because I don't want you to be lost at the very end here. It's a PDF document. I remember now. Here it is. Here, see? So, 0.5 theta and sine points of 0.5 theta, etc., etc. So, that's what I'm doing here. One over square root of 2, 0, 1 over square root of 2. Because I know the angle is 90 degrees. I don't know, minus 90 or plus 90, you can go and look, use the rule, whatever it is. And this is the quaternion representing the, is everyone with me? This is the quaternion representing the rotation for that example. Now remember, the sandwich on the other side, you need to flip the vector. Flipping means just make it minus, minus, minus on the vector side. So I made it here. Here it is 0, 1 over square root of 2, 0. So I made it 0 minus 1 over square root of 2, 0. And then I do a multiplication. Now, quaternion product or the Hamilton product is available in MATLAB. But I wanted to understand it, so I wrote my own function here. It's very simple, It's just, remember I defined the product. So basically, I just wrote down those things, It's something great. But in the MATLAB toolbox, there is a, quaternion product. Directly you provide all this. And I did it. Right? And then I did it again. Because remember, you need to do 2, right? You need to take the vector and pre-multiply, and then the result needs to be post-multiplied. Let me remind you again. Here, see? 1 and then 2. So completing the second quaternion product, and then you get the result, and then you need to pull out the 0 because you just want the vector, and I get it here. So let's see. There's the result. Remember that was the answer? So before we break, let me ask you a question. What if you take this and use a quaternion that is the opposite of that rotation that took us from the local frame to the world frame? We took the result and we applied to it the opposite quaternion to how we went from local to world frame. In other words, we go from world frame to local frame. We'll end up with the original result, right? So you can try it. It's a complete circle. So that's another way of checking that you understand quaternions. It will take it back to the original result. And then if you do it again, it will come back to the world frame. And then you do it again, it will go back to the local frame. So basically, quaternions avoid gimbal lock at the cost of one extra parameter. Actually, it's not just one extra parameter because it's 3 Euler angles. What does it take to apply that? Remember that matrix, right? You have a matrix of transformation which is 3 by 3. So it's 9 numbers. It's 3 angles, but there's 9 numbers because you have a cosine and a sine and so on. So instead of that, you're adding on one number and you're doing a quaternion product and getting the result, no gimbal lock. So it's worth it. So gimbal lock is, solved forever. All right, let's take a break for about 5 minutes, and then we'll move on to the next topic, which is localization. So that is not working because when you hit tab completion, right, a different part of the network should respond and fill out the fields. So we found out that on these computers, it's so slow that it either times out or never completes. So you don't need to do that in Ubuntu, you can do it from within MATLAB. And this morning I showed you how.
Okay.
That code has that segment that you can do it. Yeah. Yeah.
So we can directly implement MATLAB instead.
Yeah. So what I'm doing in the MATLAB program is I'm just resetting it to 0, 0, the origin.
Yeah.
But if you change the numbers, you can put it anywhere you want in the gazebo.
Okay, so
You
we
can put it in the
use
air.
today's code, the
Huh?
first one.
The first
Yeah,
one
I'm just
has.
checking.
Yeah, in fact, I can pull up that and show you. I think it was this one.
But we don't.
Yeah. So here I'm doing it just to cancel the jittering. The turtlebot tends to move very slowly, even when you don't do anything to it.
Yeah.
So I'm just trying to cancel it. So this is the way you do it. Yeah. This is the call. See this, where is the pub? Here. I'm creating a publisher for publishing to the set model state. Exactly like Ubuntu is trying to do, but it's too slow on your machines and it's not doing it. So I'm setting up a publisher with the right message type. I'm getting a copy of the message, which is set message, right? And then over here I'm filling the message.
Oh, yeah.
So I'm putting in the turtlebot 3 burger. I'm not putting in the world because I think the default is the world. But if not, you can go and look here. Which one is this? Set message. Reference frame, let's see there's nothing there, but I bet you the default is the world, otherwise it won't be doing it correctly. So it assumes that the default is the world frame. That's MATLAB. On the other side, if you leave it blank, it will give you an error on the Ubuntu side. Okay, so it's these 2 blocks. You just copy it and put it in. And then, if you want to change it to any other location, then instead of 0, 0, you can put it up in the air if you want. And it's fun because the robot will go up. So you can put 3, 4, 16 or something. So instead of 0, 0, you put anything you want. I want it to snap back to the origin, so I just put 0, 0. And then these, I just commented it out, but I said if you want to give the thing an orientation, you have to figure out the quaternion equivalent of that, and then fill it in. So these are the ABCs. Remember I said that XYZ is not really XYZ, it's like ABC. So if you want to do other orientations, if you just figure out the quaternion, you can get it. Typically here you want rotations about the 3 world frame axis, you know. You're not looking to rotate it about this or this. So it'll be easy for you to figure out, you know. You can try pointing it at 45 degrees. It'll work. And then you have to send it. You have to send it, otherwise it won't be complete. You have to send it, because if you don't send it, then that information is just sitting here. Huh?
This is not there in Teams.
It's not there? No, it is there.
This is not there.
OLCL1 is
This
not
is
there?
not there.
Oh my god.
Only the adjust heading and the Euler heading conversions are there.
I'm sorry. I'll put it right now. I'm glad somebody caught it because. Let me put it there. So I'm putting it here. No. Support material. So no wonder. Yeah, I'm sorry. There's only 2 there. Yeah, let me put the 3rd one. This one. Is it there now? Yeah, I wanted to give you this program because you're going to use this to build the other one. Because let me run through this again because I think you saw what was there, but since you didn't have it, you know, apologize for that. So what I'm doing is I'm initializing ROS, standard stuff, creating the publisher, right, for the set model state, and then I'm filling the fields and sending it. So these 2 blocks are new. You have not seen it before. The IP address block you've seen before. These 2 are new. And the moment you execute this command, the turtlebot will reset. Because sometimes you run the program and it doesn't quite get, you know, complete the thing. So you want to move it back without shutting down Gazebo and opening it or using that reset pause button. So then, this is the usual thing. I create a publisher for velocity and 2 subscribers for odometry. And then I create 2 sets of variables. One is for that straight line motion and the other is for turning at the vertex. I'm setting up the lengths of the sides and the angles of turn, except that these are not relevant anymore, right? For your homework exercise 2, you don't need this. This is just for this program. So you can delete whatever is not needed, don't leave them in there. And then I'm collecting odom to set up my plotting variables. So this is exactly what we are doing in the exercise 1. And then set up the rod straight object. And then this is the big one. You have an outside for loop that is for the 3 sides of the triangle. For you, it will be the number of waypoints you have. So you have a big outer while loop within the for loop. And the big outer while loop just wants to check whether you have made it to the waypoint. But of course, if you don't steer, if you don't point the robot towards the waypoint, it will never make it to the waypoint. So the outer while loop only works because you have the inner while loop. Otherwise, it will just go off, unless you're lucky. But you won't be lucky because you're sitting at the origin and the waypoint is here. So that will require a lot of luck, like winning a lottery. So I stop once the first, I stop, when am I stopping here? Yeah, in this case I'm going the triangle, so I am stopping at each corner. In your case, you will not be stopping at all. You'll keep moving until you come to the initial position again. Is it clear? So here I'm stopping because I'm doing the triangle. So stop after you reach the vertex, or you think you reach it because you're using time, and that's not going to work. So stop somewhere in the proximity of the first vertex, then do the same thing for the turn. So again, here the two while loops are one on top of the other because we are going there and then we are turning. In your homework exercise 2, one will be within the other. So there is a little bit of work for you to do. I think there's enough work that it's a 1 week assignment is reasonable. Because you take this and you modify it with all my hints, with the quaternion information and all that, and complete it. And then you're turning in place here. So here clearly one while loop is sitting on top of the other because here's where the while loop ends, and here's where the second while loop begins. So it's stacked one on top of each other. In your case, one will be inside the other. Your case meaning the homework exercise 2. And that's basically it. I'm plotting at the very end so that you get the whole thing as it goes to the waypoints. And then I told you about the control loop, how to set it up. You have to get the heading error, and then you have to multiply the heading error by a number. That gives you a little bit of flexibility. If the heading error is a lot, you want to catch up fast. Otherwise, it'll be just wandering, and maybe you're not correcting fast enough that you're already past the waypoint by that time, right? You can see all that, but by putting a very low reaction time, the vehicle will not come around and point quickly enough. If you put too high a value of Kp, it's going to go like this. And if you put a very high value of Kp, it actually becomes unstable because you're basically asking it to spin around. And so it will progress, but it will be spinning wildly. Any other questions on the homework exercise? So the advantage of doing it early rather than on the last night is that when you get questions you can ask me, right? But this is the norm, I think, these days, because I had a class of 25 students the last time, and there was only one girl who would come the very next day after I gave the homework assignment, having tried out something and with questions. All the other 24 would do it on the night before, and many of them won't do it right. Hopefully that's not the case with you, but so if you start early, you discover the problems and you learn more. Okay, so in the half an hour we have, let's move to localization. So let's see, did I post this? Or maybe I didn't, right? Localization? No, so let's do that. So let me create a folder. I'm going to call it localization and mapping, though we're not going to do much mapping, just a little bit discussion on mapping. Okay, wrong color. I wanted it to be green, but that's okay. I'll fix it later. And here it is. Very good. Okay. I just posted it. To give you a couple of minutes for it to complete uploading. This is the one. Okay, yeah. Did you get this? So if you have this, we'll make good progress through tomorrow. We have 2 hours tomorrow, and then next week we'll get into cognition, and then there's only sensing and perception. So we're able to see the end of this. Okay, so the 30 minutes, let's cover as much of it as we can. So I think I mentioned this in my introductory talk on the very first, was it Friday? That localization and mapping are kind of interlinked. You can't talk about one without talking about the other. So, and this is a very important task because there is no mobile robot that doesn't have to move in order to carry out its mission. And same thing with the robot actuators. It's the same thing. They have to move. All robots have to move in order to do something useful. So therefore, it makes sense to talk about not only part planning, which we're going to talk about next week, but also the need for localization and mapping. These are key ingredients. So if you have a pre-developed map, right? And I think I may have told you that there is no such thing as a pre-developed map which is 100% reliable. There is no permanently correct map in this world, except in the very trivial cases. And that's because maps can change. Typically when you're driving a car on the road, they do all the time because cars are coming in and out of view. So therefore, the map is only like the first attempt at giving you an idea of what's around you. But even if you have a pre-developed map which is not fully accurate, you need to know where you are in it. Otherwise, the map is useless. You have a nice map, but you don't know where you are on the map, it's useless. So you need localization. And then you have to look at the map in order to correct it. Now, this is particularly true if you have an earthquake situation, right? No prior map is going to be useful to you. You're going to build the map as you go because everything has collapsed. Battlefield, same thing. So as you move, you develop the map and then you localize yourself in it. That's why we have this algorithm known as simultaneous localization and mapping, because one supports the other, which supports the first one. So it's like doing one and doing the other, doing one, doing the other, and constantly, you're doing this rotation between localization and mapping. So an accurate map is needed for localization, but also accurate localization is needed to develop an accurate map. So, I just wanted to throw this in here. It looks like the classic question, which came first? Was it the chicken or the egg? And there is no answer to that question. And so there's no answer to this question, but there's no need for an answer. Because you can start with localization and then do mapping, or you can do it the other way around. But that's how it can be made to work in SLAM. So typically map development happens as the robot moves. Always, even with a known map. And SLAM is the algorithm that is the classic algorithm that's used to make these two work together. And I think I used this example in the very first class that, if you're walking into a new home and in those days, let's say you don't have a camera, and so you're trying to maybe sketch something so that your husband or wife can, look at it later, your first impression of the house. It had a living room of this size, and then the dining room door was on the back side or something. So you have a rough sense of dimension, and as you move and see more things, you start putting it on the map, but you also know where you are on your sketch map. So that's really what is going on here. It's SLAM. So here are some interesting things about maps. We have global maps and then we have local maps. And that is like a parent-child relationship. So for instance, the map of this room is very much a child, right? Because we have a map of the building outside that. And then we have a map of the campus around that. And then we have a map of Vellore outside that. And then Tamil Nadu, right? So it depends on what you're interested in. If you're never going to go off the campus, You don't really care about Vellore maps and Tamil Nadu maps, because this is the only map of interest to you. So, what is the most local map that you have? When you turn on your LiDAR and cameras, whatever you see around you and you put it on a map, that's it. That is your most local of local maps. And in fact, bigger maps are constructed from these little pieces of local maps, right? And that's why it's very important to have coordinate transformations. Because sometimes your robot is looking this way, or you can have a robot with 5 cameras, and those cameras are like human necks. They're looking around like this. So you can't put something you see when you're here at the same place when your neck is like this, right? And our brain coordinates all that, but we got to get the computer to do the same thing, and that's why we have quaternions and coordinate transformations and all of that. We've got to stitch these maps together so that you don't put a scene here right on top of this because you forgot to do the coordinate transformations. In fact, bad mapping, you'll see many examples on the internet. It'll be as if somebody is throwing paint all over, creating a mess. And finally you'll say, I can't even move because there's no room. That's because you put obstacles in all the empty spaces because you did not use coordinate transformations properly. So these are the reasons the prior map may not be reliable, because you could have accidents, road accidents, they're not shown there typically. They're getting better at, the speed of reaction, but Google Map does not show the most recent accidents. They don't have that kind of speed. A water main break, like there's water across the road, the map has changed essentially. There's a road repair. Google Map typically picks up that, but maybe not in India, because that information is not readily made available. And there can be mistakes in map creation. Mistakes is where you put a building where there isn't a building. It can happen. Moving objects, definitely not. No map does moving objects. It's for you to use in your local map. And of course, earthquake and battlefield situations, nobody has solved that yet. You have to build a map. There is no prior map available. Maybe if a drone goes over, but depending upon the resolution of the camera, you only might get a rough idea of what's going on. The drone camera might not be that powerful, so you may have to correct that map. So you see, you might start with a drone map which is approximate, but then you'll have to correct it with whatever you see. You'll train up basically. So SLAM, I'm going to walk you through this basic idea of SLAM because I like this document a lot. Perhaps I should have opened up the version on my computer, which I'll try to do. Here, let's replace that with this one. That was the Teams version. And where is my, okay, it's not playing, 1 second. I don't see all the icons. Okay. Okay. So it is a long address, so I had to reduce the font size. So some guy got his PhD, using or developing the SLAM technique. So what happened? Here it is. This is not that guy, okay? This is an MIT document. He's making fun of himself, he says SLAM for dummies. We have these dummy series books. So they're really making fun of themselves because these are not easy things to understand. By the dummies, he says. So I'll give you, there are some 80 some pages. But we're not going to go to the 80 some pages. There are some beautiful figures here that enables us to understand SLAM. I'll try to relate it to medical robotics. It's just my conceptualization at the end of this discussion. So LiDAR is the best example. So as I move, my LiDAR tells me there's an obstacle here, right? So I start off by knowing my location, I assume. And then I put, so because my LiDAR is fairly accurate, 360 degrees, 360 rays, each one spaced 1 degree from the next one, that covers the entire 360 degrees. So I'm able to take those and put it on a map, right? But I should put it on a map with respect to the robot's orientation, because the robot's orientation is going to change. And so I've got to put it on a fixed frame. It doesn't have to be the world frame, right? But the world frame is the best fixed frame, right? It is the original fixed frame. So I have to do a transformation. I see this here, I put it on the world frame, right? And then I start moving. So let's go to the pictures. So here. So this is the robot. These bolts of lightning are supposed to be, I see 3 obstacles. So I put them on my map, right? I know where I am. I assume that initially I took a GPS reading, I know where I am. And now I'm going to move. See, the robot is represented by a triangle, the stars represent landmarks. The robot initially measures using its sensors the location of the landmarks. So now the robot is moving. So the dashed line indicates the robot is moving. Now, how much you move is up to you. Maybe you want to take a look at the obstacles, more often, right? But when you take a look at the same obstacles more often, then you have more computation time. So you can't be looking at it, every step. Now, how is this motion monitored? Odometry, right? So based on your original map, so this is the original map, you have moved. So if you know this motion, even if it's approximate, knowing where they were on the original map, you should have a rough idea of what happened to these landmarks, right? Oh, that's this one. I saw it there, but now it's here. Kind of a thing, right? So now I can turn on my LiDAR again. No, not turn it on. It's always on, but I gather the data. So these bolts of lightning, right? So I think, I may have told you this. It's very important to understand the method, not the details of code and the mathematics. That comes much later. If you get into that early, you're stuck in the sand. You have to understand what are they trying to do. So my LiDAR gives me the reading again, right? And now, just by math, I should be able to do this because I have had those on the map, right? The locations I knew in an absolute sense from my previous location. But now I'm in a new location. And I'm getting new readings of the same obstacles. So I should be able to say, okay, where am I now? Because I had a map with those 3 obstacles, I know how much I have moved, so I should be able to, with the new LiDAR readings, again figure out where I am. Except that odometry is telling me I'm here, and odometry is like, as it goes further and further, it lends more and more. And finally it falls apart, right? Because my odometry cannot be relied on for a long distance. Because suppose your tire hits a stone and comes up and it's spinning, then you think you turned, but you didn't turn. Your tire went up in the air and your wheel started spinning and you racked up some encoder counts. So when you figure out where you are, from the same obstacles, you end up here. Now you can't be in 2 places at the same time, right? Are we 100% sure we are here? No. Are we 100% sure we are here? No, because the LiDAR is not accurate either. Can we just take the average? No, because LiDAR is more accurate than odometry. So that's where a technique known as Kalman filtering comes in. It is sensor fusion, but taking into account how much can I rely on this result and how much can I result on. Averaging won't do that. Averaging is you're treating it equally, right? So there is a technique that combines and says, I'm actually here. Now I don't like that. It should be really closer to the LiDAR position, unless I'm getting them wrong here. No, yeah, he's done it right. This is the odometry position. So that's the odometry position, and that one is closer to the LiDAR position. Can you get a perfect result? No. Will you be better if you use 4 obstacles instead of 3? Yes. Can I use like 50,000 obstacles? Well, first of all, you have to use the obstacles that are available there. I'm not going to bring in obstacles from outside, but when you use 50,000 obstacles, you'll have more computation time, And it'll take, so life is a trade-off, right? Life is always a trade-off. How accurate do you want to be, and how much energy you want to expend to get that accuracy. So this is the basic concept of SLAM. Then you have to do all the math and so on. I left out one piece here. You know how difficult it is to say, I saw these three obstacles there, and this one is A, not that? So they have a technique known as scan matching. Which enables an obstacle seen earlier to be attached to an obstacle you're seeing now. Because you know, those obstacles are not human beings. Even if they were human beings, a computer can't distinguish between human beings. Well, face recognition, yeah, but all barrels look alike, right? If these are just traffic barrels, you can't tell the difference, you agree? So they have a technique known as scan matching that enables the algorithm to figure out the A that I saw here, is it that or this? Now sometimes it makes mistakes. There's nothing 100% accurate. And because of that, SLAM is also imperfect. There's nothing in this world that's completely perfect. So let me tell you something. You will not get a perfect husband or a perfect wife, or a perfect son or a perfect daughter. There's no such thing. Hopefully they are mostly perfect. So life is imperfect, so SLAM is also imperfect. So as you go, you keep doing this over and over again. It's better than odometry alone. Now there's a problem, right? And here's the problem. When you go to the ocean, what happens? Everything looks alike, right? I can't say I saw this wave over there and now it's the same wave because it's collapsing all the time. Same thing in the desert, right? Everything looks sandy. So SLAM does not work in the desert very well. You have to have GPS or some other way of doing it. You have to do it like our ancestors did, looking at the stars and all that. SLAM also doesn't work indoors if you have a long hallway and the hallway looks like a hallway, right? The walls look exactly alike. You can't do SLAM. But if somebody has hung pictures along the hallway, yeah, then those are landmarks. So you need features. You need a terrain with landmarks. Landmarks are like a barrel or something distinguishing. Statue of Liberty, right? The Orissa Sun Temple. So that's unique. You need something really unique. Barrels look like barrels, but barrels it can figure out. Okay, this barrel is most likely the barrel here. But if you have like waves and sand, it's completely lost. So SLAM will not work. Indoors, if you have no furniture, you have a problem. It's better to have furniture. Something, maybe a tool chest. Otherwise you'll have difficulty using SLAM. So this is the compromise, right? This is the compromise between that dotted one and this dotted one. So this is the compromise. It's not perfect. Any questions on SLAM? No. So we have 5 minutes more. Let's go back to the PowerPoint. So SLAM is typically used where GPS is not available. You can use SLAM outdoors with GPS. So now you have GPS, odometry, and SLAM. Why would you do that? Remember, the more information you have, the more accuracy you have. But you have to ask yourself, do we really need this kind of accuracy? That's the question always has to be answered for engineering products. You just don't do it because it's fun, right? Do I need 3 of them? There's also visual SLAM. Do you know what visual SLAM is? So LiDAR SLAM is what I just described. But cameras are capable of looking at obstacles and saying, oh yeah, I saw this over there, right? So that's called VSLAM, visual SLAM. So do it only if you need it. Don't keep on piling on sensor fusion tasks because it might not be worth the cost. So outdoors, typically GPS and odometry should be enough. You can bring in an IMU for skid steer vehicles, vehicles with tires that skid when they turn, and so on. So, is there a class here? No? Oh, okay, yeah. Just give me a few minutes. So I already mentioned this. Desert and ocean are out for SLAM. And then you can use SLAM with GPS. It's called GPS aided SLAM. So you find, this is why people do research in universities. They create all these different variations and publish papers and so on. Not everybody may need it, but you know, this is the job of universities. You do know that GPS doesn't work very well in, for instance, in New York City, high-rise buildings. You know, you have a real problem with GPS, and you might have to do SLAM, right? You might have to dump the GPS and do SLAM in a tunnel. Now you have a real problem, right? Even SLAM doesn't work if the tunnel is uniform. So then what do you do? So typically, if you want a self-driving car to go through a tunnel, you wall follow. Because your intelligence tells you that I've entered a tunnel and it's like a tube structure, so I'll follow the wall, I'll follow the lane lines till I get out. And then I will pick up GPS and say, okay, I have to go there, and here I am, you know, what should I do now to steer? Because there's not, you know, within a tunnel, you don't have to change roads or intersections and so on. There's only one road that, you know, comes out at the other end. So here's the problem, is relying on GPS as a component of localization. Outages. So they're becoming more and more rare, but there are countries threatening each other with blocking GPS in the case of a war. Russia just now did it. They said we can just block all the signals. So GPS might be lost. The accuracy of GPS, it depends on what quality of GPS you have. They started with 1 meter. Now they're down to sub-centimeter, but it depends on what GPS system you have a subscription to. GPS does not provide orientation, you know that. You know, it gives you X and Y. You have to move to get orientation. So they have this nice cell phone app that I once used in China, where typically your problem is you don't know in which direction to go, right? And so you just turn on your camera and point it at a building, and then immediately it tells you whether you're facing north, south, east or west. So yeah, you can do it with the compass also, but it's nice that they can immediately identify that building and localize you. So they're using it for localization, obviously. There's visual SLAM with camera. There's also Wi-Fi SLAM. So based on the Wi-Fi signals, you can figure out, you know, where your location is from different towers. And then there is something very new that I haven't really got into. Bluetooth. Apparently, Bluetooth is, you know, short distance, right? It doesn't go long distance. But apparently, within a room or even a big hall, you can figure out where you are using Bluetooth signals. So that's known as the RTLS. You can go and check it out here. That's the same thing. The pictures that you saw in the MIT document, these are the original 2 papers. I think one of them is a professor and one is a student. We'll have to check it out. PhD, I think it's a PhD thesis. Classic papers, part 1 and part 2. This is the first papers on, and not that, you know, old, 2006. That's this century, not the previous century. Okay, let's stop here for today.